without further ado, it's a great pleasure to introduce David Conlon from Caltech, who's going to talk to us about graphs with few four cycles.
Okay. All right. So what I'm going to talk about today is a sort of development on a fairly classical result in combinatorics called the triangle removal lemma. So the triangle removal lemma is the following statement. And do shout at me. Sometimes the screen share can stop. Just shout at me if it does stop. Okay, so the triangle removal lemma is the following elementary sounding statement that any graph on n vertices with little o n cubed triangles can be made triangle free by deleting little o n squared edges. Okay, so it's a very elementary sounding statement, and actually I think when somebody first hears this, it sounds like the kind of thing that we'll just follow in some elementary way by, you know, looking at edges that contain too many triangles and deleting them. But that doesn't work. You need something a bit more than that, and I'll come to that in a little while. Perhaps one of the first signs that this is not a particularly elementary thing is that it has, as an application, it implies Roth's theorem on three-term arithmetic progressions. And this says that a set A contained in 1, 2 up to n with no 3AP has size little o n. And so this is a very, very straightforward consequence of the triangle removal lemma. In fact, so much so that I can basically probably fit it in the rest of the page here. So if you assume that you have some set A with no three-term arithmetic progression, then you can build a graph between three sets V1, V2, and V3. And each of those V1, V2, V3 are all basically copies of Z5n, say. It doesn't particularly matter, but basically it's ZCn for some C bigger than 1. Okay, and what we do is we join some V1 in V1 to some little v2 and big V2 if their difference is an element of the set A that I'm interested in, the set that I claim has no 3 APs. And I do a similar thing over here. So I join V3 to V2 if their difference is in A. And I join V3 to V1 if their difference, I've inverted, I've inverted this. So if this is in 2 times A. So basically, if their difference is twice an element of A, that's not a minus, it's a times. Okay, so why are we interested in this particular graph? The reason is that it contains a bunch of triangles. In fact, the triangles it contains are basically things that start with some V and then go to V plus A and then go to V plus 2A. So you get every element of A gives rise to some triangles. So in fact, the total number of triangles you get this way is the number of ways of choosing V, which is 5n, times the number of ways of choosing the element of A, which is just the size of A. So you get a bunch of these triangles, and it's actually fairly easy to show that these triangles are edge disjoint. So no true triangles share an edge. On the other hand, because your set A is contains no 3 APs, it's possible to show that there's no other triangles. So this is actually all possible triangles within your set. And you need to delve in and use the 3 AP condition to actually show this. But if that's the total number of triangles, then the total number of triangles is around n squared, which is certainly little o n cubed. So this is little o n cubed triangles, which implies I can delete some little o n squared edges and get rid of all those triangles. Okay, but all the triangles are edge disjoint. So that little o n squared, the number that I've deleted to get rid of all the triangles, has to be larger than the number of these trivial edge disjoint triangles. So actually, I must have that 5n times a is little o n squared, which implies that a is actually little o n. So somehow what's happening is that the triangle removal lemma allows you to boost the fact that there's at most n squared triangles to there being actually little o n squared triangles. It's not an obvious deduction, but it's a well-known thing that you can go from triangle removal to Roth using this kind of idea. And I won't go through it, but a similar idea comes up later, which is why I'm covering it now. We'll see. If I have time, I might cover it. Okay. So actually, the triangle removal lemma has several other applications. So this is the sort of standard application that you get in number theory, but it also has applications to what are called hypergraphs. So, and the standard hypergraph application is to the following function. So we have a function that was defined by Brown, Erdős, and Schoch in the early 70s. And this FNVE is the largest number of edges in an n-vertex graph, sorry, an n-vertex 3-uniform hypergraph. So by 3-uniform hypergraph, I just mean that the edges all have size 3 instead of 2. So it's the largest number of edges where there is no collection of v vertices containing at least e edges. I'll give an example in a second. So, in fact, the example is what's called the Ruja-Semeradi theorem, which is actually, basically it's equivalent to it's almost equivalent to the triangle removal lemma, which says that Fn63 is little o n squared. So what their theorem states is that you can't find 6 vertices which contain three uniform edges. So you can look at the various different ways in which you can get three uniform edges, and you could end up in a situation where you have a collection of things that all share a pair like this. So certainly there's at most 5 vertices there, so that's a reasonable option. Or you could end up with something like a triangle like this, where you have three uniform edges which form a triangle. And basically, this FNVE is just asking for the largest number of edges such that you don't have these configurations. And in fact, basically, those 2 configurations are the only configurations that matter. So this triangle, and actually, if you boil this down, the thing that matters on this side is just that you ban having 2 3-uniform edges that share a pair. So if you ban both of these things, so both this and this, then you know that actually the extremal number for this, the maximum number of edges in a graph not containing either of these, is little o n squared. There's actually a different way of stating this, which is somewhat attractive and useful later on. So this is basically an equivalent statement. But the statement is that instead of 3 uniform hypergraph, let me just say 3 graph. Any 3 graph in n vertices with girth greater than 3 has little o n squared edges. So girth usually just refers to cycle length. So what you're actually saying is if you have a 3 graph which doesn't contain a 2 cycle or a 3 cycle, then it has to have little o n squared edges. And here, a 2 cycle is, this thing is a 2 cycle because basically you sort of have an exit vertex and an entry vertex. Basically, if the 2 overlap in more than one vertex, you consider that as being a 2 cycle. sorry, somebody asked, a 3 graph is just a 3 uniform hypergraph. It's just a contraction. And this thing here is basically a cycle of length 3, because you have 3 different edges that are connected together in a cycle of length 3. Okay, so you band both these things, cycles of length 2 and cycles of length 3, and then you know that the number of edges has to be little o n squared. Okay. So there are actually lots of other applications of the triangle removal lemma. It sort of crops up in lots of different places in Ramsey theory and extremal graph theory and so forth. But let me just say a little bit about how one actually goes about proving this. So if you're trying to prove the removal lemma, you usually need 2 things. So one is what's called a regularity lemma. And again, probably many of you know this, but a regularity lemma says that any graph can be partitioned into a small number of pieces. I mean, this is a meta statement, if you will, can be partitioned into a bounded number of pieces. And when I say partitioned, I'm partitioning the vertex set rather than anything else, into a bounded number of pieces, such that the graph between most pairs of pieces is random-like, or quasi-random. So, okay, so that's the first ingredient you need. And the second ingredient you need is what's called a counting lemma. And a counting lemma, so a typical counting lemma, at least in this context, if we're interested just in triangles, is you have 3 sets, x, y, and z. You have some densities between here, say p, q, and r. Yeah. And you're interested in counting how many triangles are there with 1 vertex in each part. And what the counting lemma says is that the number of triangles, sorry, there's one more assumption. So I also need, so the graphs are all appropriately random-like or quasi-random. Then, assuming that, the theorem says that the number of triangles is approximately equal to the sizes of the 3 sets multiplied by the densities p, q, and r. So basically, it's asymptotic to what it would be if these were genuinely random graphs. And that's essentially what a counting lemma gives. And this will actually be kind of important to what we do. So you have these 3 sets, you have random-like graphs between the 3 sets, and then basically you can count as though everything was random. The situation is sort of comes from the regularity lemma. So you apply the regularity lemma to a graph, and then having applied the regularity lemma, you find some place where you have these nice densities, and then you can count the number of triangles. Then the proof of the triangle removal lemma basically is you take your graph, you apply the regularity lemma, you throw away bad pieces, so pieces that are not regular, and you throw away pieces of low density. And then if you find any triangle anywhere, there has to actually be lots of triangles left. So somehow, if you end up in a situation where you have a triangle left over between 3 parts here, then that meant that this part was quasi-random and had reasonably good density. And the same was true of the 2 other parts as well. So all 3 parts are quasi-random and have reasonably good density, and then we apply the triangle removal lemma to show that not only is there 1 triangle left, but actually there's lots of triangles left. So that's basically what happens with the triangle removal lemma. Okay. But what I want to talk about today is a theme that's been studied a lot in recent years, which is sparse regularity theorems, or the sparse regularity method. So regularity methods, as applied, tend to say things about very dense graphs. So what I mean about that is, so normal regularity applies for graphs with when the densities are close to n squared, or when they are close to 1. So you might be able to say things about what look like sparse graphs, but in practice, the densities will be something like 1 over log star, or something along those lines. But you'd like to be able to say something about what happens in much sparser graphs. So what about graphs with density n to the minus c, say? So where the densities are dropping off with the size of the graph. So here, as I said, there's been a lot of work in this, and one of the things that you get is there is something called the sparse regularity lemma. And this was proved by Hayakawa and Rödel in the 90s. It's actually a reasonably old thing. And the statement is roughly the following. So if a sparse graph has no dense spots, then there is a regularity lemma. And what I mean by this is you have your graph, it has some low density. And what you want to be able to say is nowhere in the graph, basically you don't want all the edges clustered in one small spot, because if all the edges are clustered in one small spot, that small spot could end up being an irregular pair. So you could end up that all of the edges are in just some bad part. Whereas if you have this thing where there's no dense spots, then the edges are distributed quite well throughout the graph. And in that case, it doesn't need to be that strong a thing, but in that case where there's nothing that's too dense, you can actually get a regularity lemma. And there are various variations on this theme, but they all boil down to this, and they all essentially need this no dense spots condition. Unfortunately, the regularity lemma on its own is a bit useless. You also need a counting lemma. So you can ask for a sparse counting lemma as well. And it's known that a sparse counting lemma can't hold. So it's not true in general. You need some extra condition. And typically, the extra condition is that you assume that the graphs you're dealing with are contained in some very nice graphs. So, so the work that's been done before, you assume that your graph is a subgraph of some random or pseudorandom graph. So that random or pseudorandom graph that you're working relative to, basically what you've done is you've modeled the complete graph with some random thing or some pseudorandom thing, which serves as your base. So you're within, say, GNP or G and a half. Let's say, so in the random case, for example, you're in GNP, and the graphs you're interested in tend to be fairly dense subgraphs of GNP. And then what you do is you can apply a regularity lemma to this thing, exactly because the no dense spots condition comes from the fact that it's contained within GNP, which is very well distributed. Even then, proving a counting lemma is difficult. So it is now known. So there is a theorem, that basically says that there's a counting lemma for random graphs, but it's difficult to assign who actually proved this. So there's been lots and lots of work on shifting combinatorial theorems across to random graphs. And basically, this sort of counting lemma comes out of that work. So there was work by myself and Tim Gowers, work by Matthias Schacht. These container lemma results of Balog, Morris, and Samity, and Saxton and Thomason also come into it. But as a result of all that work, we actually are able to do fairly solid things in terms of counting lemmas and regularity methods relative to random graphs. The upshot is essentially that if you're within a random graph and you want to prove some combinatorial theorem that holds in the dense world, and you want to prove some analog, then you can essentially do it using these methods. Okay. And there's also a counting lemma in pseudo-random graphs, which I won't go into so much. This is sort of, this is more myself and Jacob Fox and Yufei Zhao, but it has various antecedents in the literature. So for example, the green tau theorem can be seen in this language as being about a counting lemma within pseudorandom structures, not specifically within pseudorandom graphs, but within pseudorandom structures. Okay, so the problem with all this stuff is it's very nice stuff, but it can be hard to come up with natural applications coming from this because you're sort of restricted to being within the setting of a subgraph of a random graph or a subgraph of a pseudorandom graph. So the thing that I'm talking about today is something where there is such a condition, but you can kind of sweep it under the rug and get statements out of it that look completely natural because the actual the embedding as such is swept under the rug. So the setting is the following. So all of this is work with Jacob Fox, Yufei Zhao, and Benny Sudakov. So this is myself, Jacob Fox, Benny Sudakov, and Yufei Zhao. And the setting is basically the following. You can, so it's sparse regularity for subgraphs of C4-free graphs. So the condition that sort of gives you no dense spots and makes everything clean enough is the fact that you have no C4s. And in fact, you can also do it for few C4s. But because this C4-free condition looks quite natural, the fact that you're working relative to these graphs that contain few C4s or no C4s sort of gets swept under the rug in applications. So the main result is essentially the following. So it's a counting lemma for C5s in graphs with few C4s. So, and again, the situation should be thought of as being you have 5 pieces. You have everything, all of these are nice quasi-random graphs, quasi-random but sparse graphs. And actually the density of each of these is some multiple of n to the minus a half. That's the natural density within C4-free graphs. So each of these has density around n to the minus a half between sets of size n. There are very few C4s, so somehow the C4s are small. And if that's the case, then one can count the number of C5s in exactly the same way. If we know that these things are V1 up to V5, and the densities are P1 up to P5, then you get that the count of C5s is P1 up to P5 times the size of V1 up to V5. I'm lying slightly, actually, because what we get is not that it's asymptotically equal to, we get that it's at least something like that. There are various cutoff operations that we have to do, which only give us a lower bound instead of an exact asymptotic. Okay, so let me try and explain some of the applications of this thing. So, and why we find it interesting. So So the first application is a removal lemma. So, applications. There are lots of different removal lemmas you can prove using this. So let's state the first one. So a graph on n vertices. I think I need to make it C4-free, sorry. A C4-free graph on n vertices with little o n to the 5/2 C5s can be made C5-free by deleting little o n to the 3/2 edges. Okay, so maybe it looks slightly artificial, but basically what's going on here, the numbers are coming from the fact that you're working at a certain natural density. So this thing here is coming from the fact that if we had a random graph with density p, then the number of C5s we expect is around p to the 5 times n to the 5. And if we have p is approximately n to the -1/2, then this is exactly n to the 5/2. So saying that we have little o of n to the 5/2 C5s is just saying that the number of C5s is smaller than what it should be. And then the condition or the result, the conclusion, is that we're deleting a number of edges, which is smaller than the number of edges within the graph. So the number of edges in the graph is around n to the 3/2, but we're deleting little o n to the 3/2. So somehow, relative to the actual natural density, we're saying that if the number of C5s is smaller than it should be, then we can delete all C5s by deleting few edges. Okay, and there are lots of variations on this theme. You can replace the C4-free condition with something with few C4s rather than no C4s. A second removal lemma is the following. So a graph on n vertices with little o n squared C5s can be made triangle-free by deleting, again, the same number of edges, little o n to the 3/2 edges. This is kind of what I mean, that we can sort of brush the C4-free condition under the carpet. So here there is, I haven't actually left out the C4-free condition, it's just not there. The condition on the number of C5s is smaller, so we need there to be little o n squared C5s, but also the conclusion is stronger. We can actually get rid of all triangles, and in fact, we can get rid of all triangles and all C5s by deleting little o n to the 3/2 edges. Yeah, so Tom was asking, so when I say few C4s, in the first one, you need little o n squared C4s, exactly. And in fact, the reason that we need little o n squared here is that there's a C4-free condition sort of implicit in this, which needs this, this little o n squared condition. Okay. All right, but this statement has various applications. So one application is, again, going back to hypergraphs, we can show that fn 10(5) is equal to little o of n to the 3/2. And just to recall, this means that we have some 3 graph or some 3 uniform hypergraph with n vertices, such that there's no 10 vertices that contain 5 edges inside those 10 vertices. And again, in practice, what we're actually banning are these pairs. We're also banning these triangles because certainly a 6, if you have a 6-3 like this, then you can sort of just add a couple of extra pendant edges and get a 10-5. Plus, we're also banning 5 cycles. In fact, we're banning 4 cycles and 5 cycles. Because in any of these cases, we can sort of just increase the graph or add some extra pendant edges to get a 10-5 configuration. So in practice, what we've done is we've banned cycles of length 2, cycles of length 3, cycles of length 4, and cycles of length 5. So again, this can be stated in terms of girth. So a 3 graph on n vertices with girth greater than, girth greater than 5. Contains little o n to the 3 halves edges. In fact, there's a strange phenomenon that seems to be happening. So if you look at these 3 graphs and you have girth versus the sort of extremal number, or this, let's call it extremal number. Then what seems to be happening is, in order to have girth 3, so no 2 cycles, then you can have around n squared edges. So up to some constant, you can have n squared edges. But as soon as you go to 4, this drops to little o n squared edges. And in fact, we know that that little o n squared edges is close to being sharp. Essentially, the bare end construction shows that this is almost tight. For 5, our result shows that, for 5, where you're banning all cycles of length up to 4, there's a result of Lezebnik and Verstrata showing that the answer is n to the 3 halves up to some constant. In fact, I think they nailed down the constant exactly. Our result here is saying that little o n to the 3 halves is what happens for 6. And here we don't know. So we don't know a lower bound. We suspect that there is a lower bound here, but we don't actually know how to prove a lower bound. We couldn't find an analog of bare end for this particular situation. And of course, you can keep going. So for Girth 7, it is known that it's n to the 4/3. Both upper and lower are known. But for length 8, we suspect that the answer is little o n to the 4/3. But again, that's an open question. So extending our method so that, and I'll come back to this in a little while, but extending our method, so essentially what's going on is you want to assume that you're C6-free, and then you want to show that, prove a counting lemma for C7s, and we don't know how to do that. And again, I'll come back to that in a little while. Okay. So let me talk a little bit about the number theory applications, because this is an additive combinatorics session. So there's a couple of different statements, and again, we're sort of brushing some things under the carpet. Ryan's asking if I'm willing to conjecture. I think it probably is. I don't know how to prove it, but I think it probably does go exactly that it's at the 4/3, little o 4/3, 5/4, little o 5/4. So on. Okay, so the first number theory application is the following. So suppose A and B are natural numbers. I always leave out 0 when I talk about the natural numbers. Then every subset of 1 up to n with no solution to the equation ax1 plus ax2 plus bx3 is equal to ax4 plus a plus bx5 has size little o square root n. And I should add, what I mean here is no non-trivial solution. So there's a collection of non-trivial solutions or trivial solutions. For example, you could take x, y, y, x, y for any x and y, but you want you don't want some simple situation like that to be happening. Okay. So if that's the case, then you get little o root n. Now this is related to some result of Ruja. So Ruja in the early 90s has a couple of papers on solving linear equations. And there he defines something called the genus of a linear equation. And he shows that, so basically he shows that this extremal number, if you want to call it that, so So yeah, the extremal number of an equation is less than or equal to n to the 1 over the genus of the equation. And the genus is just the number of parts that you can separate into such that you get things adding up to 0. So for example, Roth's equation is just 1, 1 minus 2, and there's just one subset that sums to 0. This thing here, let me put in some examples. So for example, if I take A equals 1 and B equals 2, then this thing is 1, 1, 2, minus 1, minus 3. And there I can separate it into two pieces, the 1 minus 1 and 1, 2 minus 3, each of which sum to 0. And the genus is just the number of parts you can split into and get this. And Rouge's result tells you that you get 1 over the genus. So Rouge, in this particular situation, tells you that it has size at most big O square root of n. And our result improves this to get little o square root of n. We actually don't know if this is sharp. This I'm less sure about, actually. So it's open, whether in this case the answer is n to the 1/2 minus epsilon. It might actually be a power saving here. There are also some translation invariant equations at around density n, where it's unclear whether, like, 2x plus 2y is equal to z plus 3w, where it's unclear whether the answer is a power saving or not. And there's a similar thing happening here. Okay, so that's one application. Another number theoretic application is, so suppose, sorry, there's some questions there, let me have a look. I'm trying to remember what the reference is for Girth 7. So there's various papers by Erwin Jury and some of his collaborators on these kinds of questions, and I think it might be in those papers. Okay. All right. So again, let's suppose that A1 up to A4 are natural numbers, and we're interested in so in a set with no non-trivial solutions. So a set A contained in 1 up to n with no non-trivial solutions to just a standard translation invariant equation. A1x1 plus A4x4 is equal to A1 plus A4x5 has, oops, I've left out a key condition. I'll come back to it in a second. A size little o root n. So it's not just a set, it's actually a CDON set. And a CDON set, by which I mean that there's actually no solution to the equation x1 plus x2 is equal to x3 plus x4. So what this is really saying is that if I ban two things, so I'm banning a solution to the CDON equation, and I'm banning a solution to some simple translation invariant equation, then actually the answer is little o root n. And again, big O root n is easy because CDON sets have to have size root n or smaller. But what this is saying is that if you add in this extra translation invariant equation, then it drops to little o root n. And actually, you can guarantee that x1 up to x5 are distinct as well. And actually, a second point is that, like, I don't know, 2 weeks after we put up this paper, Sean Prendeville found a different proof of this using Fourier methods. And Sean's paper is very nice as well. But actually, the point that I want to make about this this particular thing is that it disproves something called compactness. So in graph theory, there's something called the compactness conjecture. The compactness conjecture there says if you define the extremal number of a family of graphs to be the max number of edges in an n-vertex graph with no subgraph or no graph from this family H, then the compactness conjecture says that if I have two graphs H1 and H2, then the extremal number of that family should be basically theta of the minimum of xn H1, xn H2. So somehow the extremal number of the minimum of the two graphs determines the extremal number of the family. I don't know if anybody actually believes this. So this is a conjecture of Erdős and Szymonovich. It's known to be false for hypergraphs, and our result shows that the analogous thing is false for linear equations. So and this is, at least to the best of my knowledge, a new result. So our result shows that it's false for linear equations, because you can take the first equation to be the Sedon set, the Sedon equation, and the Sedon equation, we know that the extremal number of the Sedon equation is theta of square root n. In fact, we can pin it down to the exact constant. For translation invariant equations of this form, so say x1 plus x4 is equal to 4x5, we know in that case that the answer is actually n to the 1 minus little o1. So the power is actually close to 1. But if you take both of them together, then the extremal number is little o square root of n. So somehow, both equations together, it's easier to find one or the other than it is to find either. And it would be interesting to explore that phenomenon more, understand when this kind of thing happens. Okay. So let me say just a very, very small amount to finish about what actually goes on in the proofs here. I'll actually probably make it sound much easier than it actually is, but you need two things. So like we said before, if you're trying to prove a removal lemma, you need a regularity lemma and you need a counting lemma. So the regularity lemma is it's basically, well, what we use in practice is actually something slightly different. We use essentially a transference principle, but you can use the sparse regularity lemma. And if one used the sparse regularity lemma, then basically you just apply Kahayakawa Rödel, which is totally fine, except in order to apply it, you need to verify this no dense spots condition. And that takes a little bit of work. But basically you can show that having few C4s is enough to imply that no dense spots condition. So it comes out fairly naturally. The second part is a counting lemma. And the counting lemma, okay, so suppose you have 5 parts and you know that there are no cycles of length 4. Then what you can do is you now know that this regularity lemma holds. So basically, the fact that the regularity lemma holds means that if I pass to some subsets of these sets, then I still have a good density of edges between any two reasonably small subsets. Okay, but I have the setup where I have these 5 graphs. They're all sparsely regular, if you want to call it that. And we have no C4s. So no C4s is actually an easier assumption. So the fact that we have no C4s allows us to construct an auxiliary graph. So we pass to an auxiliary graph. And the auxiliary graph looks like this. So let's suppose we have 3 sets. And those 3 sets, maybe if I label these V1, the 3 sets are basically V1, V3, and V4. And hidden in the background are V2 and V5. And what I do is I join a vertex here to a vertex here if there's a path of length 2 going through V2. So the path of length through 2 from V1 to V3, and the same down here. So And that gives me some graph here. And the thing that one ends up with is actually by just taking those paths of length 2, this auxiliary graph, this becomes a dense edge. So it's actually basically a dense graph edge between V1 and V3, and this is also a dense graph edge between V1 and V4. I'm still left over here with a sparse graph, but that turns out to be relatively easy to handle, because what one can do is, okay, so within V1, fix a vertex. Because this is a dense graph, I can look at its neighborhood, and its neighborhood over here is actually some reasonably large thing, and this vertex neighborhood over here is also some reason, or typically it will be some reasonably large thing. So V1 in this auxiliary graph has a large neighborhood over here and a large neighborhood over here. And then because of regularity, I can actually guarantee that the number of edges between those two sets is still large. So the number of edges is still fairly large. And that actually allows you to get a counting lemma. So somehow the lesson that underlying all of this is that if you are trying to do some counting lemma and you have 2 dense edges and 1 sparse edge, then you can actually still do a counting lemma. I'm lying on various fronts here. This works quite well if you're trying to do counting within C4-free graphs. But when you have, so going to few C4s, you need to do various cutting off operations to various cutoff operations. And by doing those cutoff operations, you end up with a lower bound that doesn't give you not an upper bound. But you still get that the lower bound is asymptotic to what it would be within a random graph. Okay, so a few points just before I finish. One is that I've talked about counting C5s, but essentially there's no big difference if I wanted to count C7s instead, or C6s or anything else. So you can actually, so you can count longer cycles in C4-free graphs as well. And the methods are actually very, very similar. But the thing that we can't do, and the thing that I mentioned earlier, is this open problem, which is count C7s in C6-free graphs. Actually, you could strengthen the thing as well. So C6-free, or you could even assume that it has no cycles of length up to 6. So you could ban everything. And even then, we don't know how to do the counting. And actually, so this is perhaps a misnomer. So what we really don't know how to do is a removal lemma. So it turns out that counting, actually doing the counting lemma or generalizing what we do on the counting front is relatively straightforward. So you can sort of extend that rough idea that I gave you a few minutes ago. The problem lies on the regularity front. So, so the difficulty is with the no dense spots condition. So somehow C4s are ideally designed to be able to show you that if you contain few C4s, then in a regularity partition, you contain no dense spots. But if we have just a C6-free condition, or even a girth greater than 6 condition, we aren't able to get such a no dense spots condition. We're still thinking about it a bit, but it seems hard. Okay, I'm going to stop there.